Hi everyone, my name is Robin Berthier and I'm a postdoc here at the University of Illinois, and today I will present a demo about the network intrusion detection system for advanced metering infrastructure. The main investigators on this project are Professor Sanders and I. So meters are deployed at large scale, but they could be compromised, and the fact that they're exposed in customer homes mean that it's easy for attackers to access them. So in addition, they could be target of interest because attackers could get access to different networks: the neighborhood area network, the home area network, or even the utility network. When we look at existing security solutions, we see that most of them are deployed at the head end of the utility, and they don't have a good visibility over the traffic among meters. And also most of this security effort is focused on authentication and encryption, and little has been done in the term of monitoring. So to address this gap, we started a project a year and a half ago about a network intrusion detection system specifically designed for AMI. What we've done was to study a specific detection technology called specification-based, where the difference with traditional detection technologies is that it's not relying on a database of known attacks or on statistical profile, but it will understand the stateful operations of the protocol and get an understanding at the application and network layers. So the advantages of our other techniques is that there's no need for frequent updates, and it can detect known as well as unknown attacks. Recently, our recent progress were to integrate this technology with a formal verification framework that enable us to use formal methods to prove specific security properties of our system. For example, we could model the checkers, and then we could model the security policy, and using an automated prover show that those two were identical. I mean, one was covering the other one. And then another big evolution on this project was to go from a single sensor to a full array of sensors deployed in different neighborhood area networks. And what I will show today is how these different sensors can collaborate with each other to detect malicious activity. So the architecture of the demo is mostly made of virtual machines. We have on the rack in the back of the room over there, the vSphere server hosting 10 virtual machines, one to host the collection engine, and then 9 others to host neighborhood area network. Each neighborhood area network hosts 25 meters. Meters are simulating using a software called Trillion Table Test Bench. This software is a meter testing software which has a full C1222 protocol stack. And on each of those neighborhood area network, we also instrumented them with our IDS sensor. Finally, we have a visualization console on this side of the room with all the tools that the security administrator would need to configure the policy and then to deploy it on the different sensors and to receive alerts and gain situational awareness. So the first step when deploying this system is to define the security policy. And for that, we developed a web application that you can see on those monitors. This configuration is based on 3 sources of information. First, we have a policy, which is the behavior of the collection engine, what kind of operations will be run on the network. Then we have the network itself with topologies, IP addresses, and access control lists. And finally, we have the meter configuration with the read and write access on all the C1219 table hosted by the meters. So we can go to see more detail. For example, this is the global view of the policy where we can specify what protocol and what kind of characteristic the policy has. So in this example, we see that TCP has been defined as the transport protocol. Any other transport protocol detected on the network will be seen as a violation. We can also enable or disable the different operations that are allowed on the network. And so you can see here the detail, the characteristics of just one operation, which is service switch or a remote disconnect. We can define the threshold, for example, the frequency at which we want to see this operation on the network. If we see more than a given number of remote disconnect, then we would flag a violation. So if we go back to the policy, now that it's configured, the next step is to use our formal verification tool to make sure that the logic is still sound and we didn't introduce any gap in the checking of the protocol. So what you can see here is a tool called ACL2, where we have implemented in Lisp all the different checkers and the security policy, and we have a theorem that prove that the checkers are sufficient to cover the security policy. So let's go ahead and run the proof. As you can see, there's the stack of function and axiom being checked one by one, and if there is any issue in the proving effort by this automated tool, it will stop and show us a trace of some possible attacks. So now that the proof is finished, we can see that our security policy is covered by the different checkers. So the next step is to instrument the different sensors in the network with our newly configured policy. So for that, we developed visualization software that will enable us to see what's happening in the network. So as you can see on this screen, we have our 9 neighborhood area network. Each of those square is one virtual machine with 25 meters, but now the system is not running. Let's activate it by clicking on the web application. And we see that all the neighborhood area network are turning into green, which means that the sensors are activated and ready to monitor the traffic. And so now let's start the collection engine to interrogate each of the meters in those neighborhood area network so that the connection will be checked and validated. So as you can see here, the collection engine in blue was detected, and the meters in yellow are appearing on screen, and each of the communication between the connection engine and the meters is being validating against the checkers, and if it appears in green, that means they respect the security policy. So to speed up the process, let's restore all the different meters that we have in our network, and we have 25 for each of our neighborhood area networks, so it's a total of 225 nodes. And as you can see, the collection engine is still continuing to interrogate each of those meters one by one. Okay, so now to show how the IDS really work, let's have some case studies where we inject attacks and see how the sensors can report the malicious activity to a console. So the first attack we launch is a compromised meter, this one, starting to run a read operation to another neighborhood area network. And this read operation is the same one that the collection engine is initiating every few seconds. But because this one was initiated by a meter and not the collection engine, we see that we have a violation with the origin not being valid according to the policy. So if we go to the dashboard on the web application, we'll see that security administrator can see the alert and then act on it. It can create an incident, block the traffic, or capture the traffic for future investigation. Now, this attack was simple to detect because the IP wasn't spoofed and the meter was compromised. But if we imagine a more sophisticated attackers who would spoof the collection engine and start to send many remote disconnect to the neighborhood area networks, that would be more difficult to detect. So let's start the second attack. Yeah, we just see now that the collection engine has been spoofed. It started to send some remote disconnect to this neighborhood area network, and because the threshold of remote disconnect allowed in the network wasn't respected, we see different alerts being displayed on the network. So if we look at the slide, those tables summarize what kind of characteristics were specifically violated by those two attacks. In the second case, we see that the frequency was violated, and then the services used this remote disconnect operation was a violation given the number of times it appeared in the network. So in summary, the specification-based sensors allows us to deploy a whitelisted network where we validate each of the communication, and everything outside of the specification will be seen as a potential attack or potential violation. The main advantage is that we can detect both known and unknown attacks, and we can also integrate a formal verification tool to show that we have strong coverage in our different checkers. So the testing was done on a realistic AMI, which is deployed on a set of virtual machines. And beyond this demo, these architectures allows students working on project related to AMI to save time going from theoretical work to experimentation, because we have now a large number of meters on which we can experiment. For example, we are starting a new project where we study how we could integrate automated response with this intrusion detection system, so that when an attack is being detected, we can respond automatically and in real time. So we are also studying how the sensors could be integrated into a key management scheme so that they could monitor encrypted traffic, and this is done in collaboration with Fujitsu. And finally, we are planning to do some technology demonstration with utility partners, and this is done in collaboration with EPRI. Thank you.